Can everybody hear me? There are people.
Yes.
Okay, thank you. All right, so today I wanted to do a couple of things. I have, if you can see, I have put a review for midterm, just a few problems. They are not necessarily, I don't try to put too many because you have already things to review. As you saw from the team midterm, I'm gonna start with something that you have already seen, all right, in your individual midterm. So it's not gonna be anything new, but I wanted to cover one of the problems because it's gonna be useful, not necessarily I'm gonna use it. So keep that in mind. I have not decided yet whether I'm gonna, I have not put the individual meter together yet. I will do this today and tomorrow. So the fact that I'm going to cover this today does not mean that it's going to be in the midterm, but it's an important concept to have, which I don't believe we had. I have taught it as examples or as homework, but I decided that we will cover it here in class, and that is in the concept or related to the concept of capacitors. And then what I wanted to do, so we'll do this a little fast because everything is going to be easy, you will see it. And then I wanted to cover today, and hopefully when we come back for a lecture or so, the solenoid, and try to figure out to develop the inductance, particularly for a solenoid. And then from there, we're moving to time-varying fields, all right? And in the beginning, a lecture or so on time-varying fields is not gonna be on transmission lines, but it's gonna be on a concept that you have seen in circuits, or you will see more, which is a transformer. And the transformer operates only if you have some kind of a change, all right? So in the electric or magnetic field, or if you have two sources on each side. And then we're moving to transmission lines. So transmission lines will start half a week in going from, but it's going to take us a few lectures to really fully engage with the concept of transmission lines, because I would like to talk a bit in transmission lines about waves that change with frequency, and then capacitance and inductance, and move from there. Okay. So today, something that you may have already seen, the first part, we have talked already about the interfaces, all right? So this is a review of what happens on an air dielectric interface. And one thing that we've said is that there are two fundamental for air dielectric interfaces. There are two fundamental relations that we need to keep in mind at the interface. That the normal component, here, as you can see, of the flux density vector, all right, so the normal dN1 and dN2 in its medium is continuous. It means, what does that mean? That it's the dN1 for medium 1 is equal to dN2 for medium 2 at the interface. That's what continuity means. All right, so as you cross the interface, the value does not change. It's constant. So that's what we say. The way we express it is that the normal electric flux vector or component is continuous through the interface. And the tangential electric field intensity is continuous through the interface. So one is flux, the other is field. The normal flux is continuous, the tangential field is continuous, all right? Now, let me ask you this. When mu1 and mu2 are equal to mu naught, so the material, are only dielectric materials, all right? Materials are only dielectric materials if mu, the mu that you see here, and I don't know how to, just a second, let me try to figure out here. Where's that? There, I don't know how to write here, but in any case, let me see. All right, in any case, if mu1 and mu2, these two are equal to mu naught, which means the two materials are dielectric materials, then in terms of mu, in terms of the magnetic response, in terms of the magnetic behavior of the material, you don't see a difference, all right? If a field is only sensitive to the magnetic behavior, it will not see an interface. Do you agree with that? So which field from the fields we have learned about two static fields, electrostatic and magnetostatic? Do you agree? Which of the two, tell me, what types of material characteristics are each of these fields sensitive to? So electrostatic fields, what do they see and what they do not see? If I have a material that has epsilon and mu, all right, characteristics means epsilon, what does epsilon mean? That the material has atoms where the positive center, which is the nucleus, and the negative electrons can be displaced, all right, under the influence of an electric field. That's what the electric means. What does magnetic material mean? It means that the same atoms under a magnetic field, not only they are displaced, so like the electrons go to the one end and the nucleus sitting on the other end, so they look like dipoles, but also the electrons start moving on these circular motions, all right? So in a dielectric, you have a dipole. Let me in fact write somewhere here because I cannot write on the other one. No, how did I do that? Okay, so in a dielectric, an atom that looks like this and has around it, say, electrons. There are multiple orbits, but I will put only one here. All right, and let's assume that you have one in this particular case. So this is positive center. And usually in equilibrium, that's how it looks. And since the electron is moving around, practically, it seems like this is neutral. When there is an electric field, all right, that comes, the electric field will come like this. There is a force of the electron, of this electron, to go towards whatever positive charge has generated this electric field, because obviously it's coming from a positive charge. So there is an attractive force, all right? If this is created by a positive charge somewhere, the electron will feel an attractive force towards that positive charge. So the electron will tend to move, but the force is not very strong to move it away from the atom, all right, and flow. So what that does, the electron is moving as close, tries to go close and change the form of this atom. So now this atom more or less looks like this. The center remains where it is. It's heavy. And the electron is going on a elliptical motion around it. And as a matter of fact, it's not going to even the motion is disturbed, is more like energy. All of the energy of the electron concentrates, and we usually show this like here. All right. So, and so there is a separation. There is no a flow of the electronic energy around the nucleus, but it all concentrates at one corner. So that looks, as I did it last time, as a dipole. It does not look like that, you know, believe me, but it's schematically, you can think all of the negative energy of the system stays here, and all of the positive energy around the nucleus stays there. That's what it means, all right? And so, because you remember how we said what we said, that when we see, when I see electric flux lines, I feel like where the energy starts and where it goes. And usually the center, this is the center of positive energy, this is the center of negative. So it looks like that. That's called a dipole. Okay, so in dielectrics, that's what happens, nothing else. And so practically, you have this dipole moments, as we say, and that's what changes the value of the field inside. And that's why inside the dielectric material, the electric field is different than the field outside. That's why we have that kind of difference in the flux density between free space, all right? Because here, if the dielectric is like that, you will have all of these dipole moments here, like this. So practically, if I wanna make it easier, it's like you have all of these dipoles that look like this. That's how we design them. Show them. All right, so all of these orient like that, and they change the flux density inside. Okay, excuse me, they change the electric field inside. This is when there is epsilon r, when there is epsilon equal to epsilon naught, epsilon r. When we go to magnetic material, okay, what happens is this is a dielectric where mu equals mu naught. So this is dielectric material. What happens in magnetic materials? Magnetic materials have mu equals mu sub r, mu sub naught, and they have epsilon equals epsilon naught. All right. What happens in a magnetic material? You have the same atoms, more or less, same kind of idea in terms of the atoms. So it starts, for example, different atoms, but I will still show them like that. And then here you have the electron, energy around it. And when there is a magnetic field that comes, and usually how are the magnetic fields? The magnetic fields, if there is one, it's going to be like this, all right? Let's assume that there is a magnetic field that is created by another current, but the material sees that. What is happening now? The electrons, in the presence of this magnetic field, they start this circular motion, all right? And their circular motion is gonna oppose this. So practically, the electrons are gonna go like this. They will start trying to move around it like that, but they create a current of the opposite direction. You remember, because the currents we have assumed, all of the currents we indicate directions, that is the direction of the positive. It's opposite. The convention has been, then when we show the direction of a current, is the opposite of the flow of the electrons. You remember that? Because it shows how the holes move, not how the electrons move. So if the electrons start moving along this direction, it creates for us, conventionally, a current that will have an opposite direction from that. All right? So this, therefore, electron is going to create, so this dipole that you see here is going to look like this. So it's going to be the center of positive and negative energy is going to be displayed. But the electrons will start moving around like this and like that, creating conventionally speaking, a current that is going to oppose the green one. So creating a current that opposes the green one. All right. Now, that is what changes the magnetic flux density inside. So this motion in magnetic materials makes them sensitive to magnetic fields, while this polarization, as we call it, this polarization in the electric materials make them sensitive to electric fields, all right? And therefore, an electrostatic field will change in materials that polarize like that in the electrics, but the magnetostatic field will not see anything, because the electric materials will not be able to create anything like that, and therefore magnetic materials, as if they are not present to magnetic fields. Okay, the electric materials are not present to magnetic fields. It's like they are like invisible. Do you understand that? So magnetic materials are invisible to electrostatic fields. Dielectric materials are invisible to magnetostatic fields. They don't see them. All right, nothing happens to the magnetic field, and if nothing happens, it's like it is not seen. Okay, so that's what you need to keep in mind. And that is, yes, you have a question?
Yeah, I'm a little confused on which way the electrons are spinning. Are they spinning in the direction of the magnetic current?
So you have to remember, this is how we indicate currents.
Yeah.
But this is not the way electrons move. For a current, you remember? So for a current that we show with an arrow like this, yeah, the electrons move the other direction. Yeah. Meaning that this green current, this green magnetic field, excuse me, this green magnetic field will force, no, this current, excuse me, I said magnetic field. So this current, there is a current that creates a magnetic field that goes. So let me write here. The magnetic field from that will be, thank you for the clarification. I was not very clear on this one. They will go down like this, like they will go up like this. All right, that's B. And that's current. So this electron in the presence of this magnetic field will start moving around. All right, but it's going to move around in a direction opposite to the electrons that created that B. So if these electrons, all right, this is the current I, so the electrons move the opposite direction, because usually currents, remember, if that confuses you, we indicate the direction of a current, but it's the direction of the holes. Here is how the holes, this is a convention we use. Here, that this arrow shows the direction of holes. So electrons, which are the real, entities that move, move the other direction. Okay, so under the presence of this magnetic field that was created by this current, these electrons here will try to move along this direction, which is, well, they will, sorry, these are electrons. If the electrons here move in that direction, these are the electrons, then these ones will move the opposite. They will move like that. Okay, this electron, which means it's going to create a electric current like this. All right, which means that it's going to try to create a small magnetic field that opposes the initial one. Small. That's what it is. So why am I saying that? So you understand a little bit physically what happens, all right? But the only thing that I want you to remember, if this is a little complex, you will see it later, obviously. But if this confuses you, remember the following thing, that electrostatic fields only see dielectric materials. They do not see magnetic materials, all right, where epsilon is epsilon naught. They don't see these magnetic materials because nothing is excited inside the magnetic material. I mean, this kind of excitation does not exist, or this one. The magnetic material is not disturbed by electrostatic fields. Nothing inside the magnetic material changes. So the electrostatic fields do not see magnetic materials, where epsilon is epsilon naught. They only see a material the moment it has an epsilon different than epsilon naught, all right, if it comes from free space. And magnetostatic, magnetostatic exactly fields, they will not see dielectrics as long as mu is equal to mu naught. So that's what you need to remember, all right? So if you have a pure dielectric and a magnetostatic field, the magnetostatic field will perform like the dielectric does not exist. It's not going to be disturbed by a perfect dielectric. And if you have an electrostatic field and a magnetic material, the electrostatic field is not going to be disturbed. So these are very important concepts to keep in mind. So with that, I wanted to say, if you have a capacitor that creates an electrostatic field and you want to change, not the plate, but you want to change the field in there so you have a change in the capacitance, the only thing you have to do is to change the dielectric in there, okay? And therefore, what I wanted here to do is to use this, we have seen that, to use this, the sense of these boundary conditions, remember how to get, all right, the capacitance of a parallel plate capacitor. We have seen that multiple times. It only depends on epsilon. In this case, was free space. Epsilon, the area of the plate, and is divided by the separation between the two plates. So the question now is, what happens if in this one, okay, I put one dielectric and see what the capacitance does if I change R with the dielectric is it just multiplies by epsilon sub r. So I can increase the capacitance by placing there one dielectric of high dielectric constant. But I increase it only linearly, all right? If I want to increase the capacitance substantially, then I either have to find a very dense dielectric, and what did I say? How high are the reasonable dielectric constants? How high they go in whatever we use in electronics? Do you remember the number I said? Was it 10, 100, 1,000, or 10,000? Was it what was the maximum epsilon sub r that I mentioned in class for materials that you're going to see in real life in electronics? Close to 15, say, maximum, all right? 12.7 for gallium arsenide, and maybe a little higher for some other combinations, exotic combinations. That between close to 10, all right? So the maximum you can do in this capacitor, in terms of increasing the capacitance, is like an order of 10, all right? But what are you going to do if you have to increase it 100 times? The material is not going to help. You have to change H or A. A in circuits is not a good thing because if you change your capacitor, you make it so big. Nobody wants a capacitor like this big for a small circuit like that small. So what do? You reduce your H. And H you can reduce down to nanometers nowadays. All right. So H is what you normally utilize if you want to reduce the capacitance substantially. Okay. What happens now if your two metals are on different, so you have a difference in dielectrics between the two. One metal, for example, that is silicon, let's assume that one is silicon. The one that I have graded with these lines is like silicon oxide. They have different dielectric constants. Silicon oxide is close to 4, somewhere between 2 and 4, depends on how you do it, and silicon is 11. What happens in the capacitance between these two conductors? Of course, it changes. How do we find that? How do we find this capacitance? The fundamental thing that we need to remember, there are two things. First of all, that if Q, all right, is the total charge, then Q divided by A is the charge density. And what we know is that at every point underneath the metal surface, the normal component of D is going to be equal to the charge density. All right, you remember that there is divergence of D equals Q. And we found that right at any point, all right, or underneath the metal of a parallel plate capacitor, your normal component of D, which is Isabel, is going to be equal to the charge density that you see here. And from there, you can find the electric field, all right, which is the charge density divided by epsilon 1. You can either go like that, or if you go into our notes for this parallel plate capacitor, you will see how we calculated it. Now, if you go all of this and then you can follow this analysis, what do you find in this? And that's what I want to come down to the conclusion. So you can really do these simple calculations, but I want to speak about the conclusion. When you have the two parallel plates and dielectrics layered, different layered dielectrics, it is similar as having capacitors, individual capacitors in series. All right. So what does that mean? Go here. If now I have, for example, this is with the one that I showed with two dielectrics, but I will show one with 3, just so you don't think it's only for 2. Let's assume that I have a parallel plate capacitor like this. In fact, I have to do it. I cannot draw like that. Let's assume that I have a parallel plate capacitor. No. Okay, I'm not going to try to. A parallel plate capacitor. And another one here. And assume that in there you have 3 dielectrics for some reason, because the two, when you fabricated the two in microelectronics, the capacitor, one metal was on one layer, the other metal was another layer. And for example, if this area is, if the area of the capacitor is very large compared to the distance between the metals, as it happens, then practically, you can assume that these two capacitors are printed on a multi-layer surface or material, or the two capacitors, which are like this, they will be printed metal lines on a multi-layer material. And it could be, for example, I'll give you a multi-layer, which is it's a silicon nitride, silicon oxide, silicon. And then you can have other silicon underneath it. That is a very realistic, this happens all the time in circuits. So you may have these 3 different dielectric constants, all right? This is 2 point something, this is 4 point something, this is 11. So in that case, and let's assume that the thickness here is H. Am I going to try to solve the problem from the beginning? No. What I'm going to do is, based on the theory that we have seen, that the total capacitance here, the equivalent of this would be the following. One capacitor as if there was a metal here, and that was only the silicon oxide, the silicon nitride, excuse me. And then there was another metal here, and that was as if here was a silicon oxide. And then there was another metal here, and that was as if there was silicon and silicon underneath it. All right, but with the same dimensions. So H1 here, H1, H2, and H3. All right, if you had, and then let's assume that you put here a voltage source. All right, so you excite A. You remember the problem we did? Let's assume that these are not connected to anything. This is equivalent to 3 capacitors in series. Okay, and that's what we have seen through the exercises as well. I mean, we did the, remember we had different kind. I gave you even more crazy metals, but they were, if the intermediate metals are not connected to anything, these are 3 capacitors in series, even if there are no metals in between. The equivalent field here is as if you had this one, which means this is equivalent, which means that the total capacitance in this problem, C total, is practically looking like this: C1 for C1, C2, C3. Which means your total capacitance, C total, is 1 over it, 1 over C1 plus 1 over C2 plus 1 over C3. Now that is very problematic. Why is that? Because it tells you usually capacitors, when we make them, we want to make capacitors to have a respectable value of capacitance. And that tells you if for some reason your metal is not exactly connected to, I mean, your metal is not exactly facing one metal, the other metal through one material of high density that we try to put there, but you have other materials of lower dielectric density, meaning lower dielectric epsilon R, your capacitance is compromised substantially. Practically, your capacitance here, it will be closer to the smallest of the capacitances. All right, so that is important to remember. So now, if you have however, a different arrangement, and I will go to this here, so that's what happens here, right? That's what we concluded. Here we had only 2 layers. But now, if you go to a different layer arrangement, so instead of having the layers, this is a more difficult one to do, but it happens, all right? That you may find even capacitors in microelectronics where you have etched inside a layer and then you have deposited some other type of material. So practically, it's not going to look as nice as this one geometrically, even physically speaking, but it is possible, either for microelectronic applications or something else, that you have one metal layer, another metal layer, and in between, your dielectric changes like across these perpendicular interfaces. In that case, it's like you have 2 capacitors in parallel. All right. So the equivalent is, as you can see here, of this one, as if you have 1 capacitor here, this part, in parallel with this capacitor. And that makes your total capacitance to be C1 plus C2. So what I have therefore as one example, here is even crazy, more crazy you want to go. What do you do in this case on the basis of the previous one? Practically, you have 1 capacitor here in parallel with a series combination. So 1 capacitor in parallel with a series combination. All right, that's what you have. You don't even have to solve it. What would you have here? 1 capacitor in parallel with a parallel combination. In series, excuse me, with a parallel combination. Okay. All right. Well, we did different things, but there are different examples that I would like you to look at them. I don't necessarily want you to solve this problem. I will never ask you to prove anything to me because proofs are everywhere. But if I ask you something, and I'm not saying it's a testing of the math that I don't even know yet, but if I ask anything, it's gonna be to use these to do something, all right? Not necessarily to prove. Even if it's nice, if you know how to prove things, because it solidifies your understanding. That's from that point of view. And the proof here is on one proof on the basis of the field, and the others are on the basis of what we found before in the example. So that is one example that I have included there. Any questions so far? Okay. With that, what now I want to do is go back to connect a little bit with what we did last time. And let me see. Last week. So also I want you to feel comfortable going through the notes on from the modules. A lot of times, if you have downloaded a note early, many times when I upload them after the class, especially to include something that we've done in class, all right, which may have not been included in the initial notes. So here, you remember we looked at the inductance of a loop that had many of an inductor that had many individual loops connected to each other. And then we found that for this case, the total inductance was proportional to the square of the number of the loops, all right, times the value of the magnetic flux density, or of the value of the magnetic flux density at the center of the loop times the area of the loop. So practically, to find the total magnetic flux through each of these loops, you take the value of the magnetic flux density at the center of the loop, all right? So magnetic flux density will be this times mu at the center of the loop. And I missed something here, like a mu, for example. Okay, I need to correct that in my notes. Let me go back here so I correct it here, because I think I may have missed a mu. There. Okay, that is H, all right? And B is, of course, is mu times H, because B is mu times H. And therefore, we need to have a mu here. Just I want to make sure. Yeah, we need definitely to have a mu. We do not have that. So it's mu. There's no, would be weird without the mu there. Okay, I will add that to the notes, make sure. Okay, so it was n squared times the value of the magnetic flux density at the center of the loop times the area of the loop, all right? The value of the magnetic flux density at the center of the loop, of a loop, all right? Get that done. At the center of the loop, for a current like that, for example. If that is at the center of the loop, and this is the radius of the loop, then B naught times pi a square gives us an approximate value of the total magnetic flux through the loop. All right, and then for this particular case, if you multiply for the individual loop, the total magnetic flux by n squared, where n is the number of the loops you have one and the other, and divide by the current, then you take the total inductance. Now, what we want to do next is the following. Let's assume that we have loops, but they are like in a solenoid. And a solenoid looks like, I mean, it has, first of all, a ferrite in there. It has a magnetic material, ferromagnetic material, rather. And the ferromagnetic material here has a mu sub r. And mu sub r here can be 10 to the 5th. The magnetic materials have very high mu sub r, all right? There is no 1 or 2 there. Ferromagnetic materials have very, very large mu sub r. When you take a class in magnetic materials, there are more than one magnetic material groups. Paramagnetic, ferromagnetic, and ferrimagnetic, and so forth. Forget about all of this for now. For us are the ferromagnetic groups. If you go, say, to the web to look for a material to use, for example, to increase the inductance, look for a ferromagnetic because that has the largest value. Other magnetic materials which are using for other purposes have different mu sub r. For us, it's a very large mu sub r. And then what do they do in solenoids? In solenoids, we have not 5 or 6 loops, but we have 100. And usually, if you see them in many applications, they will look one very close to the other, to the point that they are almost touching each other. Now, of course, the wires have been shielded with the dielectric material of some sort, all right? And so the metals do not touch. But in fact, if you see the solenoids, like the big ones, if you have seen like in old radios where they had these huge inductors, they use them also for high power. Even at the outside, they are so touching each other that they put even a kind of a gluish kind of a material to just get them stuck. And then they look like one solid thing, I mean, but they are different wires. And all of those may be, and all of those may look like this, all at and up until the end, and they may be 100, 200, 1,000, depending on how much inductance you want. Now, if you have a case like this where n is very large, it could be even 50, all right? When you have a case like that where your loops are so many and then they are so close, the magnetic field in there is not exactly the magnetic field that or the magnetic flux in there is not exactly the same with the magnetic flux we have calculated for multiple loops that may be separated. And why is that? If you have a loop here and another loop underneath it that is very close to it, but not this close, all right? So there is a small distance in between them, but not necessarily almost touching. Then there is some kind of a flux that is leaking through this, all right? And therefore, the value that you get for the total flux will not be the same. It's going to be very, very close, but not the same as if the two were even closer. Now, of course, it's a small for like 1 or 2 or 3 loops. You're not going to worry about this. But when you have 100 or 200, small changes there can add up. And you will have a small change times 200. That may be a big number. All right. So what we do to find the magnetic field in this case is the following. We start with the following fundamental problem and say, if I had I'll start with how the book started. If I have a planar surface, and then on this planar surface, I had all of these currents, let's say, that come out. These are currents. They're not, it's very similar like what we had the charges, all right, on a planar surface, but these are currents. Each one of them, say, is I, but they're like that. And let's assume that all of these currents are multiple and I cannot even measure them. It's like many multiple loops. I know the current of each loop, but I cannot measure how many. But I know the distance, the length from the beginning, from the first loop to the last. So I know the length of this planar. The currents are moving, coming out of the board, all right? And let's assume that they're just going straight. Then I can find an equivalent current density like this, which is I times, well, not exactly. I can find a total current for this, I'm sorry. Let's call this J. A total current I, which is J times L. So that's total. All right, so practically, if I have a total current that flows like that, then I can identify the current density if I divide the total current by the length. Okay, that's what you have. In that case, then, I can assume that the magnetic field that is going to be created by this current, by this flow of many, many currents, if they come horizontally out, I mean, out of the board, but along this direction, assume that this is the X direction. So X. So in this case, the magnetic field is going to go like that. Here. And then eventually it's going to run out like this, all right? But all of the magnetic field lines, it will go like that. And like this. Let's assume now that all of these currents are on a metallic conductor, on the surface of a metallic conductor, like this. So practically, they're only on one side of the conductor, and therefore there is no current inside, all right, of the conductor. There is a zero field, and therefore, what is happening there is all of the flux lines that I'm interested in are on one side. So I can, for now, assume that I can ignore these lines here. They are not of interest to me. All right, and I only care about these lines above. And let's assume that now, if this is X, this is minus Y, therefore direction, all right? This is X, positive Y will have it here. So this B magnetic flux density will be along the negative Y direction, and we have a value, would have a value. Now, what do we know? We know that the curl of H equals J. So practically, I know that at this point, at any of these points, all right, on these, very close to the current, the curl of H, which implies that this component, the AY component of H, is going to be related to the X component of J. So from this, what I find is that practically H sub y is gonna be minus j. And from there, I find that b, which is gonna be sub y, b, which is gonna be along the negative y direction, is gonna be minus ay, just to signify the direction. And it's gonna be mu, not outside, all right? Now we are in free space, j. That's therefore how we find here at one point. If I wanna find the flux, total flux, magnetic flux of this, I would have to integrate from here to infinity practically, all right? Until, because the lines will go all around. However, this is exactly the value right here. The value of this flux right at this point is that. And if I go further out, yes, they're going to change. Now, what if I want to confine this magnetic flux? I don't want it to go out and vary. If I put another metal here, and you remember how we confine magnetic? We put currents that have opposite direction, all right? That's we combine it in between. What if I were then to put here another metal above it? We'll continue that, the concept on Monday. If I put another one, and then I put here currents that come opposite direction, that go inside, all right, I will confine the field in between these two plates. And then what do I create? If I confine it between these two plates, I create a very focused magnetic flux. And then I can use this current here to find the equivalent inductance. All right? This is an inductance, magnetic, it's not capacitance. Even if there are plates, this is magnetic storage here that we do. So why do I do this? Because we're going to use this expression in the solenoid. Because if I cut the solenoid along one direction, I see this practically. All right? I see only the currents that come out of the board and the version of the current that goes in the board. If I cut along the axis of the solenoid with a magnetic material. And so we'll take it from there next time to continue. Any questions about the individual exam? I've opened everything. Yes. No. Open only everything that you own.
So is there a way to still take the exam?
What is happening to the
No,
class?
I'm not going to be in class on Friday.
Okay, can you take it online?
I have my computer. Is it
Yeah.
going to be online?
Yes,
Okay.
but you have to email me
Uh-huh.
as soon as you submit it. Remind me that you took it online. Okay.
So is there going to should I email you right now?
No, you email me after you upload it.
After I upload it. So
That you took it from wherever you were.
okay, so it's going to be under modules, right?
Yeah, I mean, like you will see your homework.
Okay.
Yeah.
You said the exam open note.
Yes.
My notes are on my computer on the OneNote. Am I on to do that, or do I need to print them out?
No, everything. I mean, you can bring your laptop. You can go
Oh, so
to the web.
I can still use my
Yeah, yes, of
Visual
course.
notes? Okay,
Yes,
thanks.
yes, you're welcome.
I think I noticed like an error on some of
Tell me.
the homework solutions.
Yes,
Right here, you have this is supposed to be QB, right?
yes.
And you define that as
Let me see. Let me go with that was a solution.
team
Individual,
homework 3.
individual 3,
No, team.
team 3.
Yes.
Okay, show me where, so I have to correct it. I'll take it, yeah.
Yes. This QB right here.
Yes,
It's supposed to be negative 1.13, I believe. Right there.
Okay, I will make a note here and then check it.
Yeah, because like here you define the QB issue.
All right, let me check it. Here. Thank you for telling me.
Thank you.
Yes.
What is the structure of the exam like? Is it gonna be
Three problems. One is going to be a theoretical question. The other from the things we covered, obviously, class. The other is going to be a multiple choice. The third is going to be a problem. 50, 50, 100.
will it be like on paper or will it be through Canvas?
It's going to be on Canvas, and then you are going to write the solution. You don't have to download it from Canvas. Write the solution and upload it. I mean, take a picture and upload it as a PDF file.
Okay. Will we be allowed to use our notes?
No, everything. You can, it's open book, open notes, everything.
Okay, thank you.
Sure.
Is the midterm because in class or is it on Zoom as well?
No, it's only in class on Zoom, only by exception.
Oh, by exception. Okay.
Yeah.
And I have another question for one of the top hats. My computer wasn't working, so I was like submitted on my phone. I didn't go through, so I emailed like top hat support about it. They said like I submitted it, but it didn't go through my phone. Like I have.
So can you send me? I know you told me about this before, isn't it?
Oh no.
No, okay. Just send me a note and be very specific. Send me an email. Be very specific. Section like 501,
Yeah.
and then which. Tell me exactly so I can go and see.
Yeah, like top hat. They investigated. They said like I submitted it, but like.
That's fine. Just
need
tell
your,
me. Write the whole thing and send it to me.
Okay, thank you.
Sure.
So you said the midterm is open note?
Everything
Okay, and then it's everything was covered to today,
up until last Friday.
next Friday. Okay, thank you.
All right.